Thank you so much. It's a pleasure to give this last talk. I hope it won't be too intensive as a last talk, but I try my best, yeah. So our story starts in 1914 when Lusin told Lebesgue he was wrong and that not all images of function of Bayer class 1 are Lebesgue measurable. However, images of continuous function are Lebesgue measurable. So it was already known that not all set of reals are measurable, and already at this time, there was a lot of question about should we use the axiom of choice or whatever it was called then, or the existence of transfinite numbers. So already there was a germ of what we are going to do today, which is, as you said, the reverse mathematics of this theorem of Lusin, that is the measurability of analytic set. So yeah, so the theorem is provable in ZFC, but so maybe just to fix ideas. So let's take, is it big enough? Okay, so until then at least. Okay, I will try harder. Yeah, so fix a real number in our setting of second order arithmetic, so a set of natural number. We say that A is Lebesgue measurable, basically if the upper measure is equal to the lower measure. So approximation from inner open set, we can fix the measure of basic open set. This approximation from inwards is equal to this approximation from outwards. And in these settings, then we have the real number that is the measure of the set. Yes. But I mean, here we have to fix these. We have to fix lambda for in our setting where we talk about set of natural number as real. But so it depends on the interpretation that you have of set of reals. So maybe this is a bit. Hmm? Oh, right. So I see the audience is still wide awake. Great. Absolutely. So yes. So set of reals in second order arithmetic, if we have open set, we have codes for them in Polish spaces, and we can define analytic set. Analytic set will be coded by a sigma 1,1 formula. Okay, so first, some facts. In recursive comprehension, we can prove that the Lebesgue measure of any basic open set exists. And, well, assuming AC is 0. And this is equivalent. Okay, so this is what we start with. And then the question that preludes our work, the fact that preludes our work, the theorem, is by you, which is a mathematician. And it proves that ATL0, within ATL0, you can develop the theory of Lebesgue measurability, and you can prove then lambda A exists for a Borel. So maybe just in second-order arithmetic, we will call Borel set by well-founded trees. So So the leaf nodes will be the basic, we call the basic open set, and each time we go up, we take the union of the complementary. And in ATL0, we can show that for all real x, there exists a function that interprets the tree at x, and that tells us the tree to 0, 1, and that tells us basically f x of the root node of the tree is equal to 1, well, if and only if x belongs to the Borel set. So if certain condition holds that make the tree being interpretable as a code for a Borel set. So we need ATL0 to speak about all of this, and then you showed that in ATL0 we can deduce the Lebesgue measure of any of these Borel codes. Okay, so ATL0, basically Robinson arithmetic, and then you add, for the second order part, the axiom that you can do transfinite recursion. And maybe a fact that I would like to highlight, maybe it gives some insight and it will be echoed later, is that if you look at, so first of all, in ATL0, we can prove that we have, for example, sigma 1, 1 choice, or delta 1, 1 comprehension. And for example, if you look at the set of hyperarithmetic reals, so basically a Turing drum iterated transfinitely for any well order, then this is not a model of ATL0. And this is because they are recursive well order, well, pseudo well order, so recursive order with infinite descending sequence, but none of them are hyperarithmetical. So someone gave a talk, the first talk was about this fact. It was from you, I think. Yeah. Yeah, and so this is important because then in this, with ATL0, if you think that you have a well order, because you cannot see with a descending sequence, then you can still construct the iteration of Turing jump around this pseudo well order. And that's what we call a pseudo-hierarchy on this pseudo well order. So in ATL0, we have pseudo-hierarchies. And this will be important. This will come up later in the talk. But so right now we have a bit of a landscape of the universe we are working with. So another thing that we have in ATL0, Bob talked about that earlier today. So in a tier 0, we can develop a theoretic interpretation. And this, from a tier 0, for example, you can do this translation between sigma 1n formula and sigma n-1 formula in the language of set theory, and you can construct models of set theory. And in particular, in a tier 0, you can prove the existence of model of basic set theory, not of model of KP. Yeah, so this will also be interesting because now we need a goal, and the goal is to prove the following theorems. So, theorem 1. In a tier 0, the following are equivalent. First of all, all pi11 sets are measurable, Lebesgue measurable. Which here means that we, well, let me finish this state. So, and pi11 comprehension. So this is an answer to a question of Simpson after this result for within a tier 0. What is the right subsystem to prove analytic or co-analytic measurability? But we also have a more nuanced version. So I forgot to mention, but so I'm presenting to you joint work with Juan Aguilera, my supervisor, and Keita Yokoyama, who works in Japan, also in reverse mathematics. And the second theorem, also in a tier 0, all pi11 sets are Lebesgue regular, and a tier, well, yes, so finite sigma 1,1 or pi11 comprehension. So the difference between finite sigma 1,1 comprehension and complete comprehension is that here we are only able to, so maybe so this is an equivalent formulation, an equivalent axiom to sigma 1,1 induction, which is not provable from a tier 0, and by finite sigma 1,1 comprehension, I mean that for all sigma 1,1 formula phi, and there exists a set X such that, and also for all n, all m less than n, m is in X if and only if phi of m holds. So there exists a set that computes finitely many answers to the sigma 1,1 question. Okay, so here we have an intermediate subsystem between a tier 0 and pi11 comprehension, and by regularity, So by regularity, I actually mean this equality, which can be proven without proving that this gives us a specific real number. So basically what we do is that this is a supremum and this is an infimum, and we prove that for all epsilon, well, these values differs only by less than epsilon. But it is not possible to prove without pi11 comprehension that this infimum and supremum exist and are a single value. I think, yeah, I think you probably think about determinacy. But it's linked, but with one level difference. Well, with some consistency things, I guess. Yeah, so let's just trust. Yeah, Lusin said it already, that it was provable in sigma 1, in ZFC at least. This is a space free of judgment. So, all right. So, okay, so we can try to prove analytic measurability, and the idea to do that is we have a sigma 1 formula, and we try to find set of reals that we can describe in second order arithmetic, and to find a covering tight enough so that we can prove that it differs from the sigma 1 set only by a measure 0 set. So there could be several ideas to get this covering, like trying to get approximation, getting this result for approximation of the sigma 1 set, and then try to collect them. But if we do that without care, then we may need to use strong axioms like sigma 1-2 choice, or I don't know, higher. So to make this machinery works, we need to put together a lot of tools that allows us to analyze analytical set in a very precise way. So the first of these tools is the Spector-Gandy theorem, or representation. Yes, so this is stated and proven in ATL 0. And the theorem is the following. Take any pi11 formula then there is a sigma 1 formula in the set theoretic language psi star, such that for all y, the following are equivalent. First, psi of y holds, and second, there exists some alpha, a well-ordered computable from y, such that L alpha models psi stars y. So, and also the mapping from psi to psi star is recursive. So here in ATL 0, we prove this by recurring to an analysis of a hyperarithmetical quantifier. And so we have this pi11 formula, and we look at it says that some tree is a well order, and to check that it is a well order, we try to construct somehow the ordinal that is computed by the well order. And so for that, we only need to look in all the hyperarithmetical set in Y. So it means that there exists an alpha computable from Y, such that at this level, some sigma 1 formula, we can find the witness of this soundness of the tree. Well, yes? Oh, yes. Thank you. Voila. Okay, so good. And now, so we want to analyze co-analytic set, and here we see that we can analyze them by looking at well orders computable in Y, for each Y that belongs to the co-analytic set. And now basically what we want to do is to erase this superscript here. And well, we can do that, but only by focusing on some kind of Y. And in the quest to do so, we need to combine it with a tool that goes well with measurability. And so now we will talk about random forcing. So we will have models of V equals L with some decent amount of set theory. And then with random forcing, we can extend them, and that will provide us with nice tools. So now let's talk about random forcing in ATA 0. So first of all, we have the forcing lemma. So the forcing lemma is saying that if you have a collection of dense set, which here, if you have it in second order arithmetic, is given as a countable collection of set, so it is countable, you will have a generic filter that contains any condition you want. So you can do forcing, basically. Well, you can do forcing on some models and with some care. So now consider the forcing condition, the random forcing condition. So B has a collection of codes, well-founded trees for Borel set, such that the Lebesgue measure of A, which is the set that the code is coding, just a notation, is strictly greater than 0. And we also quotient this by, well, if we are the same up to a set of measure 0, then we are the same. So this set doesn't exist in ATA 0, but we can still talk about these codes. And here, so the condition is stronger if you are smaller. So CB less than CA if the measure of B without A equals 0. Okay. So maybe before, well, okay, so suppose you have a model M of some basic set theory, then I will write this lemma on the following blackboard. So here we will talk about two notions of randomness, and we need a lemma to link them together. So the lemma is the following. So, but still probably in HL0, the following are equivalent. So we say that X, so for X a real, we say that X is random if X doesn't belong to A for all Borel set A of measure 0 in M. So X is M random. And this is equivalent to say that the collection rho X of the codes in M such that X is in A modulo the equivalence relation of if we differ by only a set of measure 0, then we're the same. In the algebra is M definably generic. Okay, so here, because of M, in a model of set theory in HL0 might not satisfy strong comprehension axiom, we need to look at the collection, well, the set we're talking about maybe do not belong to M. So we look at the set that are M definable, and we state this condition for this kind of set. So, right, so we have an equivalence between M randomness and some collection being generic. Okay. So this will be...
To get definable genericity.
Yes, so I mean, you look at the Borel set in M, but so yeah, but here to avoid confusion with Borel set that are in M, here we may restrict our attention to only sigma 02 set, so that we don't get. So we're sure we're talking about the same thing here in the model and outside. And yeah, here we talk about any Borel set, but yeah, definable about on the model. Because the model might not always agree on the Borel set with the exterior world in itself. So this is stated, and now we need to fix a model that will allow us to have to perform an analysis of belonging to the analytic set. So we need a model that contains as many well orders as we can. So first, let us denote by V equals L the axiom for all alpha in odd. There exists a set so that X is L alpha So L alpha can be constructed, and for all y, there exists alpha in the ordinal, so that y is in L alpha. Okay, and now the model that we want to construct, we can prove its existence in ATA0. So lemma, there is an omega model of. So I stated basic set theory. By basic set theory here, I intend more precisely, well, basic set theory, but in particular, we need to have full foundation. So contains this full scheme of foundation and delta zero comprehension or separation. Let's say that. So here we are lower, of course, than in Bob's talk. We don't have, it's not KP, we cannot have some kind of replacement, but what we can, so we can also ask D equals L, and we can also ask that M contains ordinals isomorphic to every element of WO, so the computable ordinal. Right. So why is that so? If you look at the sentence, take a well order and construct a model of this that contains this well order, this will be, so to construct this model, you will need to use transfinite recursion, and this statement that the model contains a copy of this ordinal is a sigma 1 statement. So going back to this method of pseudo-hierarchies, here we use a technique that says, okay, if for all ordinal I have a witness of transfinite recursion that satisfies a sigma 1,1 statement, then there must exist also a non-standard pseudo-well order on which I can perform the pseudo-hierarchy and get also witness of this sigma 1,1 statement, because otherwise the sigma 1,1 statement would be characteristic of the fact of being an ordinal, well, being a well order, which is a pi 1,1 statement, and sigma 1,1 is different than pi 1,1. So here, by this technique, we get provided, we get a non-standard such that LA is a model of BST plus V equals L. And then this model should contain all the computable ordinal by an argument that we could call the Wills lemma in ATA0. So if you don't contain all computable ordinals, then there is a least ordinal that you do not contain. And if you look at, let's say, B, and if you look at LB, then this is the well-founded part of your model. And you could prove that the well-founded part of such a model should be a model of KP, but then B should be a non-standard ordinal, because KP can compute every computable ordinal. So that's what we call Wills lemma in ATA0. Okay, so now we have a strong model to work with. We can we can look at random reals over this model. And now, the important thing is that we will be able to transform this theorem. And I really don't have much time. Well, did I start at 4? Yes. All right. So, so how are we gonna do this? Basically, there is something magic about being m-random. So now when I say m-random, we all know what model I'm talking about. This one is m. But when you m-random, then maybe I should write this here. If x is m-random, and y is a well-ordered computable in X, then actually y is isomorphic to some z in WO. And yeah, here we like to use this model. Okay, so this is a proper lemma that is key to our result too. So basically this lemma here allows us to prove a V2 of Spector-Gandhi representation, saying that for all y that is m-random, we can erase this. And that's a good news, because then it means we can analyze our co-analytic set by looking only at computable ordinals, but computable ordinals are all contained in our model M. And now I need to erase a blackboard. So I guess I could erase that one. And yes. Okay. If there is any question, this is a good time to think. Everything, I promise everything will make sense. Hopefully soon. At least I stated my main result. Okay, so this is important. And now what we do is that we prove regularity of, so take A, a co-analytic set, represented by a pi11 formula, phi. And what we prove is the regularity of A intersected with a set of random reals over M, because actually most of reals are random. And we can prove that the set of reals that is not random over M has measure 0. So if we prove regularity of this set, we prove regularity of A. And then what we do is that with everything we have developed so far, so take X in N, M random, then X belongs to A. So we use a Spector-Gandy representation V2 for psi, this pi11 formula, which is equivalent to the second statement. So 2, there exists alpha in WO such that L alpha of X models psi star of X. Okay, so here, if you're M random, then it means this is M generic. So you can look at the forcing extension and you can prove this is equivalent to there exists a well order in WO. And for this to hold, well, it needs to hold in the forcing extension. So we need to find some condition such that it forces it to happen. So there exists some condition, CB, that we can take in sigma 02 boldface. And in L alpha, without the X this time, such that, first of all, X is an element of the code B, and the condition CB forced by the random forcing on L alpha phi of the generic to happen. So the name for the generic. Right. Okay. So now we can look at all the elements of A, and we can look at element alpha and CB that witness the fact that X belongs to alpha. So now how do we get a covering? Well, so the end of the proof will be a bit rushed, but let me just write this last thing. So the covering, so that you know what covering I'm talking about. But the coverings will be these code CBs, basically. So what we can do is that we can ask, well, let me define the following. So let's look at the set of approximation for A defined by triplets alpha, CB, and W. I for I less than B, where B is an ordinal that can be non-standard. And now we ask some conditions. So to be an approximation, first you need to be, so to be an approximation of a length B, well, you need to be of length B, but each element must satisfy the following property. Alpha is one of these alpha, witnessing X is in A, and then you look at the L for the order, the constructible order, the least code CB showing this, and W is also a condition that you can minimize that force you that each new CB is disjoint from the other. And then you also ask that alpha is minimal. And so you start by a covering of length 1. So you just take any minimal such alpha, CB, and W. You have one Borel code. And then you extend it. There is at most one way to extend it. And at some point, this will stop because of the W, which are witness of the condition that the CB must be disjoint. And then when it stops, you have a complete covering of A. But now it depends whether or not it stopped at a standard stage or a non-standard stage. So we do a bit of dichotomy. And the interesting case comes from the non-standard case, because so this theorem also is telling you that in particular, all the witness Y that really belongs to A intersected with a random real, you will find them after exhausting all the standard stages. So if your approximation gets of length non-standard, then you will have codes that the model provide a witness saying, yes, they are disjoint code and they are included in this, but actually the model is wrong and these codes are bigger than the set. So the point where you use comprehension is when you need to split between the Borel set that are really covering A and the Borel set that are disjoint from it. And then you can prove that you have regularity. And yeah, you can prove it with finite sigma 1-1 comprehension, just to prove that you have ultimately regularity. But if you want to have the Lebesgue measure available, then you need complete pi 1-1 comprehension. So I thank you for your patience and your trust for this result. Thank you.